talk about threads today. So let's discuss the difference between processes and threads quickly. All right, so we've talked about processes quite a bit. So we know that a PCB gets its own CPU time, blah, blah, blah. So when we talk about a thread, so usually these guys are referred to as lightweight processes. And these guys share the CPU time allocated for the parent. So spawning off a whole bunch of threads doesn't necessarily get you more time on the CPU. It just allows you to have non-blocking calls that get internally scheduled by the process. So the process then kind of has its own version of process scheduling like an operating system would. Right? So when the process is getting its CPU time, it's deciding what's the next instruction that gets CPU time. You know, it might be the stuff from thread 1, it might be the stuff from thread 2, whatever it is, but all this is happening underneath that same shared umbrella. Okay? And so the problem we're solving here, as we saw last time, even though shared memory seems to work in general, because of the networking subsystem being a separate thing, it appears like we can't write to sockets that didn't already exist when we spawned a new child process. So we have some ways we can work around that. One way is we could use some inter-process communication to send the socket to we could have each child maintain their own list of all connected sockets and then use some communication, like I think you mentioned message passing, use some sort of inter-process communication, actually send that connected variable over to each child. So instead of them sharing the central thing, they would each maintain their own list of connected clients that was sent to them whenever something, so the parent would broadcast to all the child processes that new connected client when it came in, and then the children would have access to it. Perhaps a simpler approach and a more modern approach anyways, because in most applications today, you're not going to actually be creating a second process. That doesn't mean it's not founded. I mean, those things do happen today, but you know, we discussed that you can, it could be kind of dangerous for the operating system if you just keep spawning off child processes. That's taking up system resources that you maybe don't need when you're just trying to do a couple of things at the same time. So threads allow you to work with the resources that you're given as a process kind of more easily. So I'm going to go through a thread example today. So I grabbed a sample and then I added some stuff to it. So we're going to walk through this guy and then look how we can modify this for our chat server. All right, so we're going to be using a library here called pthread. All right, so these are POSIX threads. So threads they kind of have a style. So you have traditional threads. We say traditional threads. So old school threads, and then the new school threads are pthreads because they're for POSIX operating systems. If you were on a Windows machine, they wouldn't be called pthreads. They would just be called a thread because Windows is not POSIX. Windows is its own standard. But a thread's a thread from our perspective. Okay, so we'll include that library for pthreads. Now, what's interesting here is by including that library, you don't actually immediately get access to the threads. Similar to the networking subsystem, threads are actually a subsystem of the operating system. So when you go to compile this guy, you actually have to specifically tell it you want to link the pthread library in. Otherwise, it won't find the declarations for those things in pthreads. All right, so last time we had to run something with sudo. I'm not sure if we have to run this with sudo or not. I'm guessing we do not, because now we're living in our own little PCB, but we'll see in a few minutes. But when you compile it, if I don't include thread example, it tells me it hasn't heard of these things. All right, so I have to specifically link in the pthread library in order for it to be happy. All right, so one thing to kind of watch out for. So now let's go through this code and see what's happening. Is there a nice way to like minimize this? I guess that works. I wanted to just... All right. So I'm going to start off down here in main. And then we'll come back up and talk about these couple of functions we're writing up here. Okay. So in main, I've defined 3 variables, 3 integers. And we're going to do some different things to those integers. All right. So I have an x, y, and z all starting off at 0. Then I'm printing out the x, y, and z that are starting out at 0. All right. So then I'm defining a couple of pthread types. Now, what kind of animal do you suspect these are based on the name of this variable type? Structs. Yeah, so this tends to be the naming convention for structs. Using that little underscore thing there. So we're going to have a pthread struct. If I click on this guy down here, do I have a terminal open? Usually we can see this better over here. We don't have it in here. Mac. Oh, there's no manual page for it. Interesting. All right. Well, we probably could find it inside of pthreads. Doesn't necessarily matter, but I figured I would show you what's in there. They made that, well, whatever. In any case, just like we had sockets, we're going to create a couple of variables to capture our information about our threads. Figure they're like mini PCBs, that type of thing. All right, so now I'm actually creating 2 different threads here. So this is their little error checking thing. So pthread create, I'm creating 2 separate threads. The first one, I'm going to pass in the address of this guy. So my struct for that, so we could fill that in. Why am I passing in the address? Why do I have to pass in the address to this guy as opposed to just passing it in directly? How are structs passed by default? They're passed by value. So if I pass a struct into a function and I change the contents of that struct, it will not be permanently changed. So I'm having to specifically give this guy the address so he knows where to find it in memory so he can actually make a change to the real dude. Make sense? Because the result of this pthread create is going to be this thing being filled up with stuff. Okay? So when I create a pthread, I'm passing it the address of the struct. I don't know what the null is there. Let's look at what that second parameter is real quick. Oh, it's like it's an attribute thing, so you probably can attach different kinds of permissions and things like that to it. So we're using whatever the default is. Then we're passing this. This is the name of a function. All right, so this is InkX. And up here, I have a function, returns a void pointer, called InkX. All right, so this function does some stuff. We'll come back to it here in a few minutes. I have another function here called decx, or decy rather, that does some stuff. So I have 2 separate functions, and those are, so I want this thread to ultimately execute this function. I want this other thread to ultimately execute this function. All right. Now, these functions require 1 parameter. This guy requires a pointer, and this guy requires a pointer. I'm sending this guy the address of x. X is an int we defined right up here. Why am I sending it the address of x? Why the address instead of just x itself? What would the difference be? If I just passed in x, which is just an int, and I made a change to x inside of InkX, would that change be globally realized? Integers are passed by value, just like structs are. Okay, so if I want changes that happen inside of this function to be experienced down here by my regular program, I need to give it the address of where x lives so it can make changes to the real deal in memory. All right, so this is the parameter that's getting passed in there. All right, because the parameter of this guy, he takes in, what's being called a void pointer here. You probably could call it an int pointer, but my guess is that the functions that you have to pass in for pthreads specifically have to take a parameter that is a void pointer, even though you might know it's another kind of pointer. So notice right here, the very first thing we do is we say, I know that guy happens to be an int pointer. Okay, we'll come back to that in a few minutes. All right, so I'm creating a thread. I want it to fill in this struct. I don't want to use any special options. Here's the function I want that thread to run, and here's the parameter we're sending to that function. And here's the second thread we're creating. So we're creating two little worker bees that are going to call different functions. One's called InkX, one's called deckY. We could call the same function with every single one of our threads if we wanted to. All right, but this gives us an example of some stuff. All right, and this is just our error checking. If something bad happens, it's telling us there was an error creating the thread, blah, blah, blah. Okay, so after we're still kicking right here, we know we have two threads that now exist. Okay, now not only are they in existence, they're cooking. So this first guy, he's already running his function. The second guy is already running his function, or attempting to run their function, because they're at the mercy of their parent PCB as to when they actually get CPU time, right? Because now we've effectively, since we have the parent running and two threads, CPU time is split into thirds. We're talking about full fairness, something like that. All right, so if we're still alive here, we have two child threads that are cooking. And then what's the parent going to do? The parent is going to take our variable z that started off at 0, and it's just going to count it up to 100. That's what this guy does. Kind of crappy line of code, but we're not solving any real problem here. So this just does the plus plus beforehand, increments it, so it'll go from 0 to 1 immediately. Is 1 less than 100? Yes, it is. Spin back around. There's no body. Now it becomes 2. Is 2 less than 100? So this guy just increments z until it hits 100. All right. Then we're printing out that z, the incrementing of z, has finished. Now, we've already mentioned that our other threads were already cooking. So now down here, the parent process, the main thread. Okay, so when a process in a modern operating system is created, it gets created with a single thread, okay, a main thread. We can then, so it's scheduling for that one thread. When we start adding multiple threads to it, then it's scheduling for more than one thread. All right, so any way you cut it, every PCB ultimately does schedule its own CPU time. Just by default, it's splitting all of its CPU time among its threads, which is just one initially. All right, so when we say we're going to join the InkX and the deckY threads, what that's saying is the parent's going to wait for these guys to complete. Presumably the parent's done their job right here. The children are off doing important work that the parent can't necessarily move forward until that work is done. All right, so this would be kind of like a merge sorty type of thing, if that makes some sense to you. This would actually be an excellent merge sort example. Write this in a multi-threaded merge sort. Because think about merge sort. When we write it, so this is a recursive function, right? But if you're writing merge sort on a single core CPU, is merge sort very efficient at all? In fact, it possibly becomes destructively inefficient if you have a huge list of data where you have to call merge sort. Remember, every call to merge sort, you're calling merge sort twice, right? Well, recursive calls are expensive. But if we could pass this off to a thread, if you're in a single core CPU, it's not going to really make much difference, except you're not taking you're not costing yourself necessarily the huge footprint of memory, but you're costing yourself some memory. But if you're on a multi-core CPU and the library allows a PCB to schedule his threads on other processors if they're not currently busy. So if you have a quad-core machine and you have one process running that has 4 threads in it, so the main thread plus 3 additional child threads, potentially all 4 of those threads could be getting CPU time at the same time. Because one of the goals of the operating system is to keep the CPU as busy as close to 100% of the time as possible. So if the scheduler notices that 3 of the cores are not doing anything, why not throw those cores at those extra threads? Make sense? So you could really gain some performance from something like a merge sort if you're running on multiple CPUs at the same time, or even take it a step beyond that and have it running on multiple machines that each have multiple CPUs. So now we're dealing with distributed solutions to things. All right, but when we join a thread, the parent's basically saying, look, I'm going to wait for this dude, and I'm going to wait for this dude. As soon as they've run to their completion, then I will be allowed to continue forward. So the next thing the parent will do is it will print out the final version of X, Y, and Z. Now we know that Z was changed by the parent, so Z should be 100. So now we're interested in what happened to X and Y as a result of InkX and DEC-Y. Okay, so what does InkX do? InkX goes ahead and gives this is our integer pointer, so we're just converting our void pointer into an int pointer. That was optional. It would just been worse to deal with the variable as you were going. I'm not sure why they called it X pointer. They probably could have just called this X to make their life a little easier, but whatever. All right, so they just converted this void pointer into an int pointer, so it was convenient to use the variable. Then they're doing the same thing, so they are incrementing X up to 100. And then when it's done, it's going to print out X finished, X increment finished. So that's going to be that child thread that's going to print that out. And then it's ultimately going to return a value. So thread functions must return, this guy advertises he returns a void pointer. So thread functions have to, or pthread functions rather, have to have this function signature. That is a function that returns a void pointer. You can name it whatever you want, and it has to take a void pointer as a parameter. If you need to pass it more than one input, what would you do? Let's say you needed to pass it 2 integers and a string. This guy can only take in a single parameter. How would you accomplish that? Okay, so that would be kind of a ghetto solution. You can create an array and say bucket 0 is your first number, bucket 1, although you'd have to have an array of void pointers, right? If you're going to hold different kinds of values in your array. What would be the more C way of doing this? Or if you want to answer in terms of Java, you can do that as well. If you have a function that's only allowed to take one parameter and you want to pass it 3 different kinds of values, an int, and a string, what would you do in Java? How can you hand exactly one parameter to something but have that parameter contain 3 pieces of information? Object? Yeah, make an object that holds 3 pieces of information. An int, and a string. And then you could extract your 3 pieces of information from that object once you had it, right? How do we implement objects in C? Structs. C procedural language objects don't exist, so we would create a struct that had our 3 values in it, 2 integers and a string. We would build our struct and we'd pass the address of that struct into this guy. That makes sense? So just because the pthread function only is allowed to take a single parameter doesn't mean you can't pass multiple values. You just have to kind of package them up. Make sense? All right, so that's kind of a good use of structs there. So this guy's going to, well, in this case, he doesn't take in a struct. He just takes in the int. He runs that integer up to 100. Now notice he's taking in a pointer, so he's taking in a memory address. So when we say star x pointer, we are writing to the actual place in memory where x lives. Make sense? Now, we don't have to work with shared memory here because we don't have separate processes. We don't have separate PCBs whose only communication happens through the operating system. That's when we use share memory for these two separate processes to be able to share this global chunk of memory. Because now all this memory is being created inside of a single PCB. So as long as you're passing addresses around, all the threads are accessing the same memory. That make sense? All right, so this guy's changing actual memory. This is the value that lives at this memory address. He's incrementing it until it's 100. Then he's spitting out, increments finished. Finally, he's returning something, just in case you did plan on returning a value from this. But return null just says, look, I've done my logic, and now I'm done. This is how the thing exits. Make sense? So this will return null. Decrement y, probably make a pretty good guess what this guy's going to do. It's going to start y off, whatever value you pass it. It's going to give me the integer pointer version of that, and we're going to count it down to negative 100. Okay? He's going to print out, I'm done, and then he's going to return null. So in our main, what happened? We created those threads. They went off to the races. They were getting scheduled however they're getting scheduled. It's out of our hands. The parent went and did his logic. Then the parent said, I'm going to wait for my two child threads to finish. Once they're finished, I know I should have fully modified versions of X, Y, and Z. Right? I modified Z myself. One of my children modified X. The other child modified Y. Then we'll go ahead. So this blocks. Right? This does not let us continue. This is waiting until those threads have completed. Those threads are still running. So it's not like our program's not doing anything. This just blocks the parent from taking a step forward until the children are done. We don't have to do that. For instance, in our chat server, would we want to do that? Does the chat server itself care when a child process has finished? No, because that thread, his whole purpose in life is to read in from the user and broadcast to everybody else, right? The parent, what's the parent's job? To stand by the phone and spawn off new threads, right? With the socket that came in. So we can pass it the address of that socket. Now, maybe we want to pass it two pieces of information in our chat server example. We'll talk about that in a minute, because it might need to know the socket that he's attached to, as well as the array of connected sockets. So we might need to throw that into a struct in order to pull that off, because we need to pass two pieces of information inside of one piece of information. Okay, so then in the end, we're going to print out the value of x, which should be 100, the value of y, which should be 100. The value of x, which should be 100, the value of y, which should be negative 100, and the value of z, which should be 100. So compile this again. Make sure you use the pthread that's linking pthread into this program. And when we run this, here's our values when they started. This is the parent saying I'm done. This is the y child saying he's done. This is the x child saying he's done, the x child thread. And then and the parent waited for these guys to finish. And it just so happened that the parent finished first. I mean, the parent didn't have to finish first, right? The other ones could have completed first. We'll look at that in a second. But notice the final values is x, y, and z from the parent's perspective have permanently changed. It's the parent that's printing those out, right? So he's noticed the global changes on x, y, and well, the parent changes z himself. But he's noticed the global changes on x and y from the two child threads. All right, so threads make reasonable sense? Okay, so now we could come up here and make the parent do a lot more work. Maybe the parent's going to count to 100,000. Parent actually still finished first. We need to give it more work than it can finish in its allotted time. We could print, and that would definitely do it. Then we'll so. All right, that'll make the parent run a lot slower than the child. In fact, actually, we probably can do it. Oh, here, let's run it this way first, and I'll see if you can tell me how we could do it maybe without printing a zillion things. All right, so Z finally finished. Okay, those guys finished somewhere up here. Somewhere way up there. They finished somewhere way up there. I don't want to scroll anymore. They finished a while ago. What if I had switched this to just 10? Think the parent would still finish last? It actually surprises me the parent didn't finish last that time. Set it to 100. Oh, gotta compile again. Very interesting. What happens when actually, it does make sense. What happens, so this is I/O, right? We're printing something out. What happens to a process when it needs to do input-output in terms of the CPU? Yeah, he context switches out of the CPU. Can any of his child threads run while he's off the CPU? He can't, because this PCB is in charge of scheduling his own threads. He can only do that when he's on the CPU because he's allotting his CPU time. Now, he might have the ability to have some of the threads run on a different CPU, but if one's not busy, but only when that thread's actually on the CPU. So when we took a break here for this guy to jump off the CPU, his other threads were not running. So when he came back onto the CPU, we picked up where we left off. So we actually would probably find there's some sweet spot number here that we'd eventually hit that would say, here's your total CPU time. So I think, we bump it to 1,000, and we're not going to try to get super precise with this. Finished last that time with 10,000. All right. So somewhere between 1,000 and 10,000 spins through there. The parent is deciding that it's its child's turn, and we would presume the child's going to get its job done in its single cycle, probably. Its single allocated time on the CPU. So it would then finish. Okay. So questions about thread stuff. What would happen if I didn't do this join? So if I comment this guy out, and let's go ahead and actually, this will be an interesting experiment. Let's just do it at 100. Let me actually initially, I'm just going to cut this. We'll just initially do its normal count like he did before. But now we're not going to wait for the children, which means the parent is going to immediately come down to this print statement and print out the value of X, Y, and Z. What do you expect the output of this to be, or possibly be? Hopefully we've seen from the last couple of minutes we can't necessarily predict because we're making a guess at how it was being scheduled. So 0 on X, 0 on Y, or 100, possibly if the children are getting some CPU time in there, we might see X and Y being something, but not 100, since we're consistently seeing the parent finish first. Yeah, so we have 0, 0, and 100, because the parent processes have not run yet. So I'm going to go ahead and let's kick that up a little bit. Okay, there we go. So now we see that, well, I counted high enough that there was technically an interruption there where the thread that was counting down on Y got to run, but the thread that was counting up on X did not. See? It probably did. It probably did all the math, but then when it went to print, that requires a context switch. So if we were able to pick up where we left off, when it came back in, it would then finally do its print. Its print would, because its print is queued up by the main thread to finally get I/O time. So it looked like it had enough time to get its logic and then said, oh, I have to do I/O. Let the parent know that I've done as much as I can do. You can go ahead and have your CPU time back. The parent then presumably finished his run, which is actually probably what actually happened here. Is the parent ran as far as it could, then gave its CPU time to Y. Y finished its job in less CPU time than the parent was willing to give it. Y then said, I want to print. Parent said, okay, well, that takes time, so I'm going to take the rest of the CPU time back. I'm going to do the rest of it. Then I'm going to hand it off to X. Well, the parent finished before it actually gave the CPU time back to X for it to do any of its work. So with that in mind, we can probably, if we keep tacking numbers on here, we're eventually going to get past the size event. All right. There. So now both of them were able to, to squeeze in their runs. But it's interesting with threads because, you know, timing becomes an important thing, right? Now, our example we're looking at here kind of relies on this idea that the parent has to wait for the child to finish their work before they can move forward. So that would be kind of the example that we would see like in a merge sort, correct? You know, if the parent gets the original list and then says, okay, this thread's going to work on the first half of the list, this thread's going to work on the next half of the list, go and do your work. You know, if that's what is if that is what is happening, that parent can't just continue on and say, I'm going to do my merge step now and put my two partially sorted lists together before the two children have done their work. It needs to wait for the two children to finish doing their sorting in order for the parent to then move forward with confidence and say, I know I'm merging two partially sorted lists. That makes sense? Otherwise, we're just playing with fire and hoping the timing works out. you might have like partially sorted lists or something, and then you won't have a functional sort. So if you are relying on something to finish, you're going to have to join that thread, so you guarantee that you wait for it to finish. All right, so let's go back to our design thing then here. And let's, well, I guess we can modify, well, let's use a new one because we're gonna re-implement this in terms of threads. You'll be able to use most of what you've already written. We're just going to be doing this in terms of threads rather than a fork. All right, so our server, so this is a child thread. This is the child thread. Now, what do the child threads do? Child threads are going to receive two pieces of information, right? So this guy is going to, this was our socket, correct? So he's going to receive a pointer to S2. We also want him to receive a pointer to our shared memory. Those two things. All right, so technically we have another link here. And the way we pull that off with threads is we're going to have to put these two guys inside of a struct. All right, so let's look at an example of structs. We'll build a sample one here. I'll just steal some starter code. Oh, still on here. All right, so up top here, I'm going to go ahead and I'm going to create a struct, and we're going to call this, why don't we call it a client thread struct. All right, and now this is our, call that guy CT there. These can't match each other because this is actually your initial variable of that type. And we're not actually going to need an initial variable, but we'll leave it in there for right now. Now, we want this guy to hold two pieces of information. We want it to hold a socket ID, right? So it's going to hold a int pointer, socket ID, something like that. And then it's also going to hold a another int pointer, which is going to be to the beginning of the array where your sockets live. Call this guy list of connected clients. All right, so we'll just fake it here for one of our guys here. So we're going to go ahead and we're going to create one of our client threads. And we're going to pass that guy into InkX here. So I'm going to go ahead and, well, I need to go down a little farther. I'm going to say int pointer AR is equal to malloc 100 times size of int. So I've created some memory, right? And I've stored that inside of my int pointer AR. And then I'm going to go ahead and I'm going to create a client thread. And if we're wanting to keep with our naming convention, we might do something like that. Client thread T for type. All right, and we're going to say that this guy is, we'll call this CT1. Then we'll say CT1 dot socket ID. We'll just pass that guy X. So socket ID is a pointer, so we need to give it the address of X. And then CT1 dot, what I call AR? No, connected clients, right? Connected clients. So this guy is expecting a integer pointer. Okay, so for a list of connected clients. So what will I pass it here? AR. Why not star AR? I passed it star X, or I passed it, I'm sorry, why not the address of AR? I passed it the address of X. What's the difference? X was defined like this, so X is a int. AR is an int pointer. Int pointers hold what kinds of values? They hold addresses. That's what this guy expects. He expects a memory address. If I were to print out star AR, what would that print out? Just out of curiosity. If I were to do a printf %d \n star AR, what would print?
What's stored in
bucket 0. The value at bucket 0. Okay, because this is saying base base address AR plus nothing, which is the base address AR. Give me the value that lives at that. That's star AR, right? So this would print out bucket 0 of AR, which I think we've seen when you create a new one, it's got a 0 in it, but whatever lives there, that's what would print. Okay, so now we have our CT1 filled up with some stuff. So when we create our parent thread here, I'm going to actually go ahead and pass it CT1 for the X guy. And then inside of here, I'll go ahead and change this guy to void pointer dot, what I call it, socket ID. Because we know our void pointer is actually a struct, correct? And I want that struct's socket ID, which is going to be a, well, it actually already is an int pointer. So I can say that. Otherwise, it's an unnecessary cast. So he'll be an int pointer. If I wanted this to work a little bit nicer, I probably would say something like client thread pointer this. Give me the socket ID from that. So we're saying X void pointer is actually a client thread. I want to get the value of that client thread and read that guy's socket ID, which is an int pointer. Store that here, and then all the rest of the math should just work. All right, so let's go back down. Let's put our weight back in here. And we can just put this back to 100. All right, so now when we create our InkX thread, we're still passing it exactly one parameter. We're just passing it a struct this time. And that struct happens to have the value of X, well, happens to have the address of X stored in there, as well as the address of our array, which we're not currently using, but this is like the sample that you would use in your chat client. Ruh-roh. Didn't I name it that? List of connected clients. Oh, 1 second. We actually can call it the same thing. I think we can call it the same thing. This is the actual variable name. This would be like kind of like the class name. CT1. That should be right. That guy's right. Oh, I need to create it as a type of struct. Yeah, that's what I was saying earlier, that this guy is not required. That just gives you an initial variable. Okay, so that is in standard lib.h, right? Man, malloc. Standard lib.h. Okay, expression. What are you upset about? Client thread undeclared. Because I renamed it to this. It's that kind of guy. I think we're good now. No. Do I have to mark it as a struct there? I don't think so. The answer seems to be yes. And that one is int star pointer. Oh, I didn't save this. All right, let's get this working at the beginning of next class. We'll write our client thing with this, so I'm just using struct syntax wrong. So we'll go ahead and update what we wrote in class from last time to have our to use threads instead of PCBs, and then we won't need to use shared memory because we can just pass the address of the thing. We just need to be able to pass it as a struct. All right, I'll see everybody on Friday.